In this lesson, we will be solving a system of linear ordinary differential equations. So we can rewrite this problem in a matrix form. So let us denote the derivative of y this way, and now we will take the coefficients of y1 and y2 and write the matrix in this form, multiplied by y. So now we will consider this problem. In order to solve this problem, we will need to calculate the determinant of this matrix and find its eigenvalues. So the eigenvalues can be found with the help of, if we denote this matrix A, we'll compute its eigenvalues this way, where I is the identity matrix. And this should be equal to 0. So if we write, we'll get the determinant of the following matrix: 3 minus r, negative 2, 2, negative 2 minus r. And now we can compute the determinant. If you are not familiar with the determinant formula, I will be posting a separate video as well as sheet on it. And now you can see that this will be equal to r squared minus r minus 2 equals to 0. So we now have to find the roots of this equation. So I can compute the roots with the help of discriminant, but let's use Viet's theorem this time. If you're not familiar with Viet's theorem, then I will post a separate video about Viet's theorem. So now we can see that r1 plus r2 is equal to 1, and r1 times r2 is equal to negative 2. So from here, r1 will be equal to negative 1 and r2 will be equal to 2. So now we will have to plug those values and find the eigenvectors for each of those values. So if we plug r1 into this matrix, so here's what we'll get: 3 plus 1, negative 2, negative 2 plus 1, 2. So we'll get here 4, negative 2, 2, negative 1. Okay, so now we will need to reduce this matrix to row echelon form. And in order to reduce it, we can do the following operation: r1, that is the first row, subtract 2 times r2. And we will get 0, 0, 2, negative 1. So let's now swap those two rows. And when we swap those two rows, we'll get 2, negative 1, 0, 0. So we can then compute the eigenvalues with the help of this equation. So let's denote the first element A, the second element B equals to 0, 0. So we will have 2A is equal to, or 2A minus B is equal to 0. Then 2A will be equal to B. Okay, now let's choose a value for A. Let's say A is equal to 1. So if A is equal to 1, oh, here I messed up this equal sign a bit. Okay, so 2A equals to B. This is what we get. A equals to 1. Let's choose it. Let's choose. So our first eigenvector will be equal to 1 and 2. That's it. Now we'll need also to compute the matrix for the second eigenvector. So we just plug again, and we will get 3 minus 2, negative 2 minus 2, negative 2, 2. So we will get the following matrix: 1, negative 2, 2, negative 4. So once again, we will reduce this to reduced row to row echelon form, not reduced row echelon form. So we will get 1, negative 2, 0, 0 by subtracting 2 times the first row from the second row. So we shall do the same step as we did here, and we can also write this in an augmented matrix form. And in linear algebra videos, I will separately show techniques with augmented matrix. So let me write it here, augmented matrix. So we'll just need to write this as A times 2B is equal to 0. And A will be equal to 2B. So if we take B equals to 1, we'll get the second eigenvector, and it will be equal to 1 here, and 2 times 1, 2. So this is our second eigenvector. And now we will just need to plug those values, and we get an arbitrary constant C1 times e to the power of, let's say this is e to the power negative t times the first eigenvector 1, 2, and then plus c2 times e to the power of 2t times 2, 1. So this is how we solve this system, this homogeneous system of linear ordinary differential equations. Thank you for watching.